Model Extended XAFS data, we use Feff calculations for the photoelectron scattering factors. Because the XAFS equation is inherently nonlinear in the parameters for the near neighbor distance and other parameters describing the local atomic structure, we also use standard nonlinear least squares fitting procedures for refining the parameter values to best match experimental data. This leads to a range of topics to discuss about how to fit data. Hi, I'm Matt Neuville, beamline scientist with the Center for Advanced Radiation Sources at the University of Chicago, running an X-ray microprobe beamline for X-ray absorption and fluorescence spectroscopies. This presentation is part of the video series on the fundamentals of X-ray absorption fine structure and part of the virtual XAFS summer school at the Illinois Institute of Technology and Advanced Photon Source at Argonne National Lab. In the previous video, we talked about using Feff and showed a simple fit for one shell of iron oxide. In this video, we'll review some of that and talk about the nonlinear least squares fitting procedures, and then continue with the iron oxide data fitting two shells. We'll also discuss some about what parameters can be fit and some about uncertainties, and give some hints about modeling disorder. After this video lecture, I strongly encourage you to go through some of the demonstration videos for fitting XAFS data with Feff calculations. Links for these are given in the description below. So to start with, we're going to review the XAFS equation here. It's a bit of a large mess. There's a sine function that's 2kr showing the oscillations as a function of r, and then these terms, again, F and delta, the scattering photoelectron scattering phase amplitude and phase shift. These are strongly energy dependent or dependent on K, and they give the sensitivity to atomic number for the scattering factors. These functions are also non-trivial, and so we use Feff to calculate these functions, F and delta. Lambda is the mean square or mean free path for the photoelectron, telling how far it can travel and coherently get back to the absorbing atom. And the sum here is over scattering paths, and that may include multiple scattering. Although it's complex and not linear in any of the parameters we're interested in, well, I guess it is linear in coordination number, but if we know these F, delta, and lambda functions, then we can extract R, N, and sigma squared. So in this video, we'll talk a little bit about how that's done. To model the XAFS, then we'll parameterize this XAFS function. This will be the model that we use to model data. And in the XAFS equation, we have these terms, and those are turned into fitting parameters, or path parameters, as we call them, in Larch and other analysis programs. And here are the physical meanings for those. So here, since we're starting with a calculation that's had a structure implicit when we gave a cluster of atoms, for the Feff calculation, we're refining the distance. So we'll vary delta R, which is the change from the R effective that the path started with. In principle, any of these parameters can be varied in the fit, and we will vary them, but also, as we'll discuss, we can place limits, bounds, constraints on them as well, between different paths and so on. So in our first shell modeling that we showed in the previous video, we started with rock salt, a near perfect octahedra of oxygen coordination around an iron atom, and we refined, here's our first shell fit. Then, just as a reminder, the red curve shows the fit using F and delta for iron oxygen scattering at about 2.1 angstroms, and here are the refined values that we get for those parameter values. And the fit shown in R space here, when we look at the fit in K space, we see this is the best fit. As we discussed in the previous video, yes, this really is the best fit because we ignored all those higher shell components, all those higher R components. And here's the fit where we use the real part of the Fourier transform as well as just the magnitude. Although it's most common to show the magnitude what we really fit is the real parts, which have oscillations, and we need to match those oscillations correctly. And so the fit here is actually pretty good, and we get parameters that are not too bad, especially considering, I think, the challenges of that data set that we've been playing with. So let's talk about what we did to do that fit. So in general, fitting data requires making a model for that data. We have the XAFS equation as our model, so that makes it convenient. We have something that we can we have a model that we can parameterize. And we want to adjust those parameters, R and sigma squared and so on, to best match our measurement. So what do we mean by best match? Well, we use the chi-square statistic. Unfortunately, chi-square is the common term used in statistics. It's not to be confused with the XAFS chi, that describes how good a match is to data. So we have our measurement, chi, the XAFS measured, and then we make a model for it from the XAFS equation. And here this parameter, this x, is meant to describe all of the parameters that we might vary in the fit. And then we have an uncertainty in the noise level of the data. And we'll take the data minus the model, square that, and divide by the uncertainty in the data, or the noise level in the data. The sum of that over the number of data points gives us chi-square. And the fit will try to adjust the parameter values, here x, each of them, until chi-square is as low as possible. So the best fit is the one with the lowest chi-square. And we have a number of fitting points, an estimate of the noise level, and x is the parameters in the to be varied in the analysis. So the questions you might ask are, how do I know how many measurements I have? What is epsilon, and what are the parameters I can or should vary? In fact, if we look at this equation, we have all of the symbols, every single symbol in this equation, n fit, chi measured, chi model, x, and epsilon, kind of needs to be discussed. We don't. In principle, for Statistics 101, this is obviously the right way to go. But how to apply this to real data, say XAFS data, gets a little messy in what we mean by every one of these terms. And we'll discuss that in a bit. We'll start with, how do I know how many independent measurements I have? And this is an important topic in XAFS. Actually, in any oscillatory signal that we want to learn about, the number of parameters that can be reliably extracted from a signal is limited. It's basically the length of the signal in K, how many oscillations we have, times delta R, how much of a frequency range we want to consider, and it's 2 pi times delta K delta R over pi. If that looks like Heisenberg's uncertainty principle to you, you're right. If it looks like Shannon's information criteria to you, you're also right. These are related. It's not limited to thinking about data that's Fourier transformed. It's limited to thinking about data that is oscillatory and has a finite band. So we're not, although we measured mu of E in energy space, we're not thinking about the energy measurements. Each of those energy measurements, you might argue, is an independent measurement. But it's an independent measurement of mu. It's not an independent measurement of the local atomic structure around the atom that's doing the scattering. In fact, we have a much limited range of parameters, say 10 or 12 for typical XAFS data, that can be determined from the XAFS data. Because the data is oscillatory, there is not an infinite number of data points. And collecting more data is really just more finely sampling the oscillations, which is a good thing to do and will reduce the noise level. So it's not a bad thing to do. It just doesn't give you more independently adjustable parameters about the local atomic structure. So the fit statistics and confidence in the measurements we make really need to reflect this. And so we typically oversample our data by quite a bit. We have many more data points than we fit. But then if we're going to reliably relate our statistics to one another, we should make sure that we're scaling that correctly. So the XAFS community typically does this by using this number of independent points, NIDP, which is 2kr times delta r, delta k delta r over pi. Sometimes you'll see this with a +1 or a +2. If the +1 or +2 matters to you, then you're probably at the limit of what the data can tell you. And I won't go into like that argument or discussion. It's about that number. Not exactly that number. Here, where I have pulled this out of the sum, I've assumed that epsilon is constant. And in fact, as I'll show, we won't make that assumption any longer. So leaving that epsilon in the sum over data points is a fine thing to do. So when we fit, the goal is to reduce chi-square. So this statistic here, the single statistic here. But we often use other goodness of fit statistics because as we change the number of variables, the number of things which we're varying in the fit, we'll want to be able to use chi-square or other statistics to compare whether one fit is better than another. And so there are several statistics that we can use for that. They're all sort of related to chi-square. They usually start with chi-square and then make some adjustment for how many independent points and how many variables we have. So reduced chi-square is by far the most common. We scale this by the degrees of freedom, so the number of independent points minus the variables, the number of free parameters that are left. Using this is quite a good statistic because in general, chi-squared reduced is meant to be, from Statistics 101, again, something close to 1, on the scale of 1. We'll often find it slightly bigger than that, partly because we don't have a perfect estimate of epsilon, and partly because the model that we make with Feff calculations are not perfect. Those F and delta functions are good, but they're not perfect. In addition, we have because those statistics are somewhat questionable about whether they're really perfectly scaled, we have other goodness of fit statistics that we use as well. The R factor being the most important, because this is the misfit in the data, so the sum of the squares of the residual. These are both arrays, so there's a sum of squares, and then divided by the data instead of some uncertainty in the fit. This gives a fractional misfit, and so is the easiest to interpret. We can get an R factor of 0.1 or so, meaning that the fit is good to 1%. That's a very useful statistic to be able to relate. There are other information criteria, including the one from KK, that are also weight by the number of variables or the number of free variables as to account for the degrees of freedom in the fit. This AIC is also reported. There are other ones as well. There's the Bayesian criteria, which is actually pretty similar to this. And it's useful to use these. When comparing fits, you'll usually see that the best fit, or between different fits, you'll decide that the best fit is the one with the lowest chi-square, reduced chi-square. It's often also the case that AIC and the Bayesian information criteria that are similar to that are also the lowest for that fit. But if they differ, then that might suggest that the differences between successive fits that may not be very significant. And so you might be at the level where it's hard to tell one fit is clearly better than the other. Again, for a good fit, chi-square reduced reduced chi-square is really useful because it should be, in principle, 1, according to general statistics. That assumes that we have an accurate measurement of epsilon, which never really happens, but it's often still about within only a factor of 10 or so. So how would we estimate the noise in data? Well, for sure, in the analysis, which we'll go over in some is covered in some demonstrations, you could, in principle, say what the uncertainty in the data is, as if you measured lots of different spectra, averaged them together, you could get an average and a standard deviation in the data itself. And doing that is a good thing to do. But even for a single spectrum that doesn't have that estimate of the uncertainties, we can estimate the noise in chi of k or chi of r using a Fourier transform. So as we show here in our typical plot, if we plot out to 10 angstroms, there isn't much signal past 10 angstroms. So if I plot that same data for iron oxide, now here on a log scale for chi of r, and out not to 10 angstroms, but out to 30 angstroms, we see that the noise level, the signal is basically dropped to 0, again, because of lambda and the 1 over r squared term, and the sigma squareds in the XAFS equations. And so the data out here past about 15 angstroms is probably all noise. That would say that it's white noise that is independent of frequency, but we can get an estimate of that easily because we can easily take the sort of standard value, mean value of the signal past 15 angstroms and extrapolate it down to the data range that we're using. This high R portion of chi of R, so we can use the high R portion to estimate the white noise in the data. This works reasonably well. Actually, it works pretty well for sort of noisy data that you might think is a little bit noisy. This often is a pretty good estimate. And so we do this, we used to do this, this used to be the only way we estimated noise. And this is easy, so this is easy to do, and we do this regularly. But we also know that it misses an important component of the noise, which is to say the uncertainties in the background subtraction. When I showed the background subtraction in the processing video, or if you look at the demonstrations for that or play with the data yourself, you'll see that as you change the background parameters, you can change the data, especially in the log R region of the spectrum, significantly. And we really ought to account for that. That's part of the uncertainty in what chi of k is. In fact, if we do that and I show not only, if I propagate the uncertainties from the fit, that is, we've fitted some spline coefficients to get the background. And when we do that, we can get uncertainties in those spline coefficients and then propagate those for what would be the uncertainty in chi of k itself. And we can do that. And in fact, here's what we see for this iron oxide data that I'm beating to death. Here's the signal is now in red, and the uncertainty delta chi times 100, blown up by 100, is shown in blue. And what's most interesting about this is it's not 0, so it's above 0, so it's finite. There is actual noise in that, but also there's some oscillatory part to that. So if I plot that in R space, now the uncertainty in the data, of course, it's mostly a offset value, so there's a high-low frequency component or zero frequency component, but there's a little bit of oscillation right at about 2 times RBKG, which I think is interesting. It might be an artifact of the spline. It might be something that we should really look into to see if we can improve. But at this point in our analysis journey, we have this function that is the uncertainty in chi of k. And we really should use that. So in fact, we do use this now. If we can, if it's available, we'll use this in the fitting. So in fact, if I show you, if I make in the background subtraction that was discussed in the processing video, if I change RBKG to a half an angstrom or 0.7 or 0.9 angstroms, then these are the resulting uncertainties. And it always seems to peak up at something about twice RBKG. I think that's a function of the kind of spline we're using. So we can use, and again, we use this, and this has this, as you can see, there's a pretty enormous impact on what the uncertainty in the data is. And so we now, by default, use this if it's available. So if you've done the background subtraction in the same process as you've done the you're doing the fitting, that uncertainty will be available and it will be used in the fitting with Feff calculations. So when we reported our values for our single shell fit, we had n that was something like 5 plus or minus a half or so, and r was 2.09 plus or minus 0.01 angstroms, and E0 was 1 or something volts plus or minus a half of a volt. It's very important to use the uncertainties in the data and the best fit or the best chi-square value to estimate the uncertainties or the error bars in the fit variables. All of those parameters need uncertainties. they need to be reported at all times. It's I should say that this is just a matter of reporting data in science, that it's important to report all uncertainties in parameters or data that you extract. Oftentimes in casual conversation or even science conversations, uncertainties are sort of implied. When you say you'll be there in 10 minutes, you don't mean that you'll be there in 300.0 seconds. You mean you'll be there in 10 minutes plus or minus a couple of minutes. Or maybe you mean you'll be there in 20 minutes plus or minus a couple of hours. When you say plus, I'll be there in 10 minutes. But so that sort of uncertainty is implied. And but for the kinds of parameters we're reporting for XAFS, you might be able to say that in general, R is going to have an uncertainty of around 1/100th of an angstrom, and N is going to have an uncertainty of around 1. E0 will have an uncertainty of around a half to 1 volt. Those are useful as ballpark figures, and they might be what you get, but you should really be in the habit of reporting uncertainties, or be ready to report them at least in the supplemental material for your paper. So let's talk about how those error bars are found. If we do a fit, you can think of parameter spaces, or if you have two parameters, we'll call them X and Y. X and Y. Without loss of generality, those could be N and sigma squared, or they could be N and R. Two parameters that we're doing in any kind of fit. They could be the centroid and the amplitude of a Gaussian function. So the best the best fit values are where chi-square is the lowest. So that's x0 best and y0 best. If we move away from those best fit values, so if we increase our x parameter by a small amount, then if we go to the place where it's x0 squared plus 1, that's generally what's called the 1 sigma error bar, which is what we're reporting here. It's important to remember that when that happens, you can't just move x0 chi-square out, or move the x parameter out a bit until chi-square increases by 1. You need to also allow for the fact that the other parameters, like y0, might respond, and so also adjust that. And so the parameter, or the uncertainty of the parameter, so delta x, is not to here, but out to here, whereas this ellipse, in general, it will be an elliptical shape, is the response. It shows the response of y0 for moving x away from its best fit value. So it's generally elliptical, and the slope of that ellipse, or the slope of the main axis, is basically the correlation between the two parameters. If x increases, then y will increase in response. If x decreases, y will decrease in response. Some will have a correlation that's negative, and some will have a correlation that's positive. And this is important to consider. This is important to have considered, because for XAFS, R and E0, both affecting the phase, R being the period, and E0 being where k equals 0, both affect the phase, and so those are highly correlated. And in sigma squared, both affecting the amplitude, are also highly correlated, generally at the 85% level or so. So including this correlation is important. It turns out that the error bars that are reported by Larch and XASV or Artemis and Sixpack and so on take this into account automatically. So you don't have to think about this. It's just important to recognize that this is happening. The parameters, the uncertainties in the parameters reported do take into account the correlations. So given this plot, so in this description, increasing the chi-square by 1 assumes that we have a good fit. So it assumes that reduced chi-square is 1. So in fact, we usually have reduced chi-square for about 10 or so. So in fact, what we really do is we increase chi-square by reduced chi-square to estimate the error bars. This is sort of saying that we got a chi-square reduced of 10, and that must mean that we had the error bars off by a little bit, because I think this is a good fit, and really reduced chi-square should have been 1. So just adjust the error bars in the data until reduced chi-square is 1, and then go through this process. So just in general, we report chi-square and reduce chi-square, and the estimated error bars increase chi-square by reduced chi-square. The reported uncertainties, again, do include the effect of correlations. I'll also say that more rigorous methods or more brute force methods or exploration of parameter space around the uncertainties or the best fit values are available in Larch in the Python code and can sometimes be useful. It turns out that in my experience, actually XAFS data is pretty well described by this description. You'll see in many literatures that people assert that error bars are not statistical or are non-Gaussian and so on, and so that other processes need to be considered. In my experience, we have these tools available, and in my experience, it rarely makes a big difference for XAFS results. But you're free. If you're interested in doing that, you can contact me or leave a comment in below, and we can describe how to do that in more detail. Okay, so fitting. So we're not done with our chi-squared description, because we also need to talk about the data. Okay, so again, we took our raw measurements, turned it into mu, turned the mu into chi by subtracting the background, but we didn't really so far we haven't really said what our measurement is, and that is we usually fit not chi of k, but in R space. So we're fitting in Fourier transform space. We can fit in k space. You can fit in R space. You can fit both. The main advantage of fitting in R space, as we saw with the iron oxide data, in fact, is that we can make a band pass, a window here, and select which shells to ignore. Actually, select which frequency components to consider. So we'll fit the chi of R, both real and imaginary parts, not just the magnitude, because this gives much more meaningful fit statistics. We know that we're not, but by doing a band limit, by fitting in R space, we know that we're not trying to fit all the spectral features. So that best fit that we had for iron oxide for shell was clearly the best fit because we ignored all of these higher shells. So for our data, we can also consider that chi measured is not just a single spectrum or even chi of R that was created with a single k weighting. We could k weight in different ways. We could window function in different ways. We could include multiple data sets and refine multiple, say, data taken at different temperatures, where we know that most of the parameters should be the same or will have a simple temperature dependence, including, say, sigma squared. And that way, we would not be fitting the XAFS, a single XAFS spectrum, but fitting a group of XAFS spectra. So as long as we can model all of those kinds of data, multiple data sets, multiple k weightings, maybe k and R space together, then we can use all of those different ways of mapping the data as the data that we model. Then we can get a better fit. So all of those things are possible. But for now, let's go back to our simple shell, our simple fit of iron oxide. And look at the second shell fit. So here is the fit with two shells. Again, the data in blue and the fit with an iron oxide and an iron shell in red. And the fit statistics are here. That R factor is about 0.01. Reduced chi-square is about 3. Our coordination numbers are a bit off. We get about 4.5 and 14 instead of 6 and 12 as we should have. The distances are a bit contracted, actually slightly expanded from what we expect. Again, I think that this data might have some ferric iron in it as well as ferrous, pure ferrous iron. FeO is hard to get purely ferrous. One thing that I'd like you to notice, though, is that we adjusted E0, but we didn't adjust it independently for the two shells. We had one E0 value that we adjusted, and we used them for both paths. So that would make sense. You want to have one E0, but I've tied them to be the same. And so again, this is a pretty good fit, even if it's not perfect. That's okay, because the calculations are also not perfect. Chi-square reduced about 3. And we can look at this data this fit and this data in the same way we did before. Now here's the fit in k-space, and that looks much better. We're still missing some of the highest frequency components. If I go back, we're missing all of this stuff at 4 and 5 and 6 angstroms. And that shows up as the really high frequency components that we're missing here. If we look at the separate components, we have the iron oxide scattering here with low frequency components, and then iron-iron. And as you can see, the iron oxygen has a lower frequency. It's lower R. R is the frequency. It's lower R than the iron-iron. And you can also see that the iron oxide amplitude, it has sort of an envelope function that peaks up at lower k than the iron-iron. And that's the effective F of k. F of k for higher Z elements peaks up at higher k. So that's exactly what we would expect. There is some overlap. So if we plot those two paths together in R space, they're both now in sort of a grayish line, you can see that there's actually fairly considerable overlap between those. That iron-iron scattering really leaks down into the iron oxide shell portion of the spectrum, and the iron oxide also really decays strongly into the iron. So the fact that we went back, I'm just going to go back, because the fact that we put a little window function here was based on the observation that there's sort of a minimum value at, 2 angstroms or so. But now, as we look at this, we can see that that's kind of accidental. There is iron-iron scattering over a wide range, and iron-oxygen scattering over a wide range. So we really want to be careful about where we say a minimum in the data implies a minimum or the break between two shells. In fact, we get a better fit here shown in the real part of chi of R. We get a better fit once we include the higher shell. We get a better fit for the iron oxide once we include the iron-iron. And if we really wanted to get the iron-iron really well, we'd probably need to include the paths here, which are actually mostly triangular. And then there's another single scattering path here at, I think, 3.8 or so angstroms. I'll also just remind you that here this peak for iron oxide occurs at about 1.6 or 1.7 angstroms. The distance is 2.1 angstroms, not 1.6, and that's because of the phase shift, the delta K. If you remember from the theory talk, delta K has a slope of about -1. That gives it, with the 2kr, that gives about a half angstrom shift in R for each peak. So for both the iron-iron and iron oxide, both the peaks are shifted down, so they're not at R, they're at R minus about a half an angstrom. That's not good enough. That's not good enough to figure out what the distance is, but it's good enough to guess what the distance range ought to be. It's about a half an angstrom shift. Okay, so let's talk a little bit about what we can vary in the fit, our parameters that we're going to vary in the fit. In the XAFS equation, we have 4 parameters. Actually, there's more. E n times sigma squared times S0 squared, R, and sigma squared for each path. But the number of independent points is low. So for 1 angstrom, so for 1 shell, we have about 8 independent variables. That's okay, as long as we don't get too many paths. As we go out further in R, we'll need more paths, and we'll hit this limit quickly if we tried to model the data out to 5 or 6 angstroms. So for simple structures, it's okay to fit like this structure we did. It's okay to fit this for each path, all 4 of those for each path. But for more complicated problems, we need a way to limit the number of parameters. We might want to impose relationships between the parameters. Like we might want to say that the E0s are the same. And we might want to say that the ends or the distances are not independent. So in Larch and Artemis and all the other programs in this family of analysis tools, the path parameters are not very directly in the fit. The n, r, and sigma squared. They're all written as mathematical expressions of generalized variables, which allows us to have simple constraints. So in the code that you would write if you were going to do this in code, or the code that's generated by the GUIs, a path has an E0 that's taken as a parameter, as a expression, E0, and then a parameter, also called here E0, is guessed. with an initial value of 1. And we can use the same expression for two different paths. So this one variable will be used for the E0 value path parameter for each of those, for both of those paths. We can also say, if you want to make a mixed coordination shell, you could say that there's some fraction of sulfur in and some fraction of oxygen, and those two compete, so they are not independent. They add to 1. So you could say that you have an S0 squared value. That's your S0 squared parameter that you've found someplace else. Maybe it's 0.8, so you make a parameter for that, and you tell it to not be varied in the fit. And then you have a sulfur fraction that's a half. And for 1, you could say that the amplitude, the S0 squared term, is S0 times S frac. And for the other path, it's S0 squared times 1 minus S frac. So you have a complete mathematical expression capabilities for setting up paths. You can also do more complicated things, like you could say that the temperature dependence of sigma squared goes as what's called the Einstein model. So sigma squared Eins is a function of a single parameter theta and then a temperature. And you could say that for different temperature data, that a single parameter theta should set the sigma squared values for each of those parameters. I'll show you this in just a second. So with this, this allows you to use prior knowledge to consider more complicated problems. So you could force R to be the same bond for data taken from different edges. If you have data from multiple edges, you could say that the distance needs to be the same between two atoms. Or you can model complex distortions, like say the height of a absorbed atom above a surface. I'll also say, it's just off screen here, but each parameter can have upper and lower bounds. So each of these parameters that are guessed, you can also put upper and lower bounds on them, say, to ensure that sigma squared is positive. So an example of this would be to take a multiple data set with data at multiple temperatures. So for copper, we have some data that's taken at 3 different temperatures, 10, 50, and 150 Kelvin. And I can model all of those data together. I can say that so I have one shell, but 3 data sets. So in principle, I would have 12 parameters, n, r, sigma squared, and E0 for each one. Each 4 parameters for each of the 3 data sets. But I'll say that E0 is the same for all temperatures. I'll also say that S0 squared is the same for all temperatures. I'll say that R is linear with temperatures. So there's a slope and an offset. So there's 2 parameters, slope and offset, give all 3 distances. And then sigma squared is described with 1 parameter, the sigma Einstein function as mentioned before. Sort of fit range and so on. And we can set that up. The whole script isn't here, but it's available if you're interested in the examples. And we'll guess that the theta parameter is around 250 degrees Kelvin. And when we do this fit, we get fits here, the amplitude, but then the real parts for 50 and 150 Kelvin data. The fits are very good. And what we've determined from this is the amplitude function, the S0 squared. I asserted that n was the known value of 12, and so I adjusted S0 squared, the theta, the Einstein temperature, evaluating Kelvins. That's actually about what you expect for copper from heat capacity data. A delta E0, that's the same for all paths, and then a slope and an offset for the distances. So it's very, very shallow temperature dependence for the, these are mixed up, but very shallow temperature dependence of R, but not 0. So I know I'm going a little bit over on time on this, over longer than I want, but I want to talk about one more aspect of data processing or data analysis, and that is that in all of the discussion so far, we talked about disorder for each path as a single sigma squared. This is not necessary. It's a simple thing to do, but it's not necessary. Why I showed it was because it's a simple thing to do. XAFS is a measurement of billions of snapshots of local structure. So we have typically on the range of 10 to the 9 to 10 to the 12 photoelectron per energy point in a spectrum. So really there are billions of snapshots. Each absorbed X-ray generates one photoelectron. That photoelectron lives for about a femtosecond, much faster than the thermal vibrations of the sample. In XAFS measurements, typically 10 to the 4 to 10 to the 10 X-rays absorbed per energy point, perhaps more. So we're really seeing a snapshot. Each event sees a snapshot, and then we average over those snapshots. So far, we've put all of that into a single sigma squared value. In fact, that should be account for not only thermal disorder, but static disorder. So if that octahedra for your metal oxide is distorted, that could be part of sigma squared. You could put a different path for each of the distances. If they're close enough together, if they're below 0.05 angstroms, it won't make any difference. You could also use a sigma squared to describe that. So sigma squared can include thermal and static disorder. There's really no difference in the model because the XAFS actually doesn't separate them out either. But in general, we don't have a sigma squared, a single Gaussian distribution of distances around the atom. We have a partial pair distribution function. G of R is the probability that an atom is some distance away from the absorber. So your pair distribution function might look like this, which is not quite Gaussian. It's got a longer tail on one side than the other. The longer tail might be on the low R side or the high R side. So there's a couple ways we can handle this. To fully account for the disorder, we really should take like an ensemble average of our simplified. I slowed the XAFS equation down, and I kept this as I2KR instead of the sine function. We should really average that. That's really what we're doing. So X is the average over billions of snapshots over the pair distribution function. R won't change much, so we'll neglect that. So we could pull the 1 over R squared out, but we still get a thermal average of e to the I2KR, or sine KR. Each path in the sum now has G of R with respect to, needs to be taken into account. So you could really average over G of R. A simple way to do this, and a simple way to encode this, is to use what's called the cumulant expansion, which relates the ensemble average of an exponential to the ensemble average of X, the moments of G of R. So you'll get the centroid, and you'll get the second moment, the sigma squared, and you'll get higher measurements, skewness, kurtosis, and so on. So that's easily described as this mathematical function where we have these coefficients, the cumulant coefficients, Cn. If we look at those in a slightly more detail and relate them to the moments of R, then C1 is just delta R. That's the ensemble average of R. Actually, it's R minus R0. Yeah, R is R minus R0, or centroid, or based from the Feff calculation, R effective. So the centroid. Sigma squared is the ensemble of R squared minus the ensemble of R squared. There's a third term, a third cumulant, and a fourth cumulant, and you can go higher. In general, we find in the XAFS literature and the XAFS community that the third cumulant can be important in many cases. The fourth cumulant is available in the programs, but it's hardly ever actually useful. What we find more common is that if the cumulant expansion doesn't work, if the structure is disordered enough that adding a third cumulant isn't good enough, then you want to go to doing something more complicated, or build a model for what G of R is directly. So you can also build a model by making a set of paths that are spaced in R, say at like 0.2 or 0.25 angstroms, and then model the amplitude for each of those paths. For each of those paths, you would set sigma squared to 0, and you would just add them up with an amplitude that goes as your G of R function. One way to do that is with following the GNXAS code, which is designed for studying liquids and very disordered systems, which uses like a function that's an exponential times power law, and gives a function that looks like this. So you could just create 10 paths spaced at 0.2 angstroms and use that as the amplitude term, where now R0, the centroid, and then a sigma and beta parameter are the parameters that describe this this distribution function. Okay, I think I've gone much longer than I was hoping to have to go for this lecture. I know this is one of the hard parts. So let's talk. So to wrap up, using Feff to model XAFS mostly means paying attention to a few things. The number of independent points. There's not very many parameters that can be varied separately, given a limited K and R range of the spectrum of interest. Always look at the uncertainties and report the uncertainties of the parameters. Don't just report or look at the best fit values, but always check that the uncertainties are reasonable, and that if a parameter has a huge uncertainty, that probably means that it's not very well constrained. And you should check or require in the fit that sigma squared is greater than 0 and n is greater than 0 and so on. Try to make the model physical. And you should think about how you might combine parameters for different paths, ideally making a physical model that describes the structure that you're studying, not just for first and second shell or so on, varying n and r and sigma squared for each path separately will work. But if you're trying to really model complex systems where you have to include 5 or more paths, you may need to really think about a physical model that describes the structure. Try the third cumulant now and again. It might be needed. Actually, you will sometimes find that if you just it's easy to add. You just add the third cumulant and see if it gives a value that's significantly different than 0 outside of the error bars, and if it improves the fit, improves reduced chi-square. So if adding a third cumulant makes reduced chi-square go down, then you needed it, and that's important. It will be highly correlated with R and E0. It's a phase term, and so it might alter a little bit the distance that you get out. And for very disordered systems, cumulants might not be enough, and you might need to use one of these histogramming or other techniques for modeling G of R. Okay, more information on X-rays and X-ray absorption can be found at the links shown here. And I hope this was useful. And if you have any comments or questions, please leave them in the comment section below. And I hope that you're now ready to go on and do some actual demonstrations and trying of fitting yourself, and now can make sense of what the programs are doing and how to interpret the results. So good luck with fitting, and see you in the demonstration videos. Thanks.